Okay guys, here's a warm-up. Put me on pause, give it a shot, and then let me show you how it works. Go ahead, hit pause now. Which quadrant will be completely shaded in the graph of the inequality y is less than or equal to 2x? Understand that this is the first quadrant, going counterclockwise, second, third, and fourth in Roman numerals. Y is less than or equal to 2x. The less than or equal to knows we're going to have it's going to be a solid line versus a dotted line. We also know that this is a linear inequality, so my slope is equal to 2 over 1, and my y-intercept is equal to 0. So if I start at 0, my y-intercept, and I go up 2 to the right 1, up 2 to the right 1, or down 2 to the left 1, then I connect it with a solid line because it has the equal sign. Something like that. We know that no matter what side this is shaded on, it's not going to be this answer and it's not going to be this answer because you can't shade both sides of this line to get quadrants 1 and 3 completely shaded. So let's pick a test point. Remember how we always used to use 0, 0? We can't. So let's go ahead and use 2, 0. If I substitute 2, 0 in, does this come out true or false? Is 0 less than or equal to 2 times 2? Is 0 less than or equal to 4? Well, that is a false statement. So this side that I picked my point on is false, which means this side is true, which means I shade everything from this line all the way across the true side. So which side, or which quadrant is fully shaded? It would be quadrant number 2. So that's the answer. Okay, we're going to do 9.7, which is linear, quadratic, and exponential models. We've talked about these in brief. Linear is what we do a lot of in 9th grade. We do quite a bit of quadratic, and we just touch on exponential. Linear equation is usually in the form of y equals mx plus b. They also could write it in standard form, which is ax plus by equals c. Or they could do it in point slope, which is y minus y1 is equal to m times x minus x1. 2 out of the 3 of these are actually on your reference sheet. Remember, m stands for slope and b stands for y-intercept. A quadratic equation is in the form of y is equal to ax squared plus bx plus c. That's a complete quadratic. If it's missing one or both of these terms right here, then we would call it an incomplete quadratic. Quadratic equations always form parabolas on a line. The only ones that we're going to deal with this year is the parabolas that open up, and that's when your leading coefficient is bigger than 0. If it's smaller than 0, it opens down. These are the only two, positive and negative. These are the only two types of parabolas that we are going to deal with. This is the one where you guys have to do the axis of symmetry and the vertex, min and max. Remember the formula? X equals negative b over 2a. That will find you your axis of symmetry, which is what cuts the parabola in half. Exponential is in the form of y is equal to a times b to the x. Notice that the variable x is in the exponent's position. That's why we call it exponential. That's when your curve actually gets fast at a very quick speed. The rate goes at a very fast speed, whether it's going exponentially growing or exponentially decaying. So if you see x as the variable as the exponent, we know it's going to be an exponential function. In the graph, if it looks like it's going up or down incredibly fast, exponentially, then we know it's an exponential function. Okay. Choosing a model by graphing. Let's look at these 3 scenarios. Graph each set of points, which they have done for us. Here are the points, they graphed it. They want to know which model is most appropriate for each set. So if you graph these ordered pairs and they plot out like this, we know that it's in the shape of a U. So therefore, this is going to be a quadratic equation, which is in the form of y is equal to ax squared plus bx plus c. If you were to graph this set of points, or this relation, and it plotted the points out like this, as you see, notice that the curve is going up pretty fast, at a pretty fast pace, so it's going to be exponential. That's in the form of a times b to the x. These are the parent functions. In this situation, you have 4 points. If you were to graph them, you should notice that they line up. So that means it's linear. And the most generic or standard parent function we look at is y equals mx plus b, though I actually like point slope better. The y minus y1 is equal to m times x minus x1. I think that tends to be more handy, but that's personal preference. Identifying using a table. Linear, this is a little bit tricky, and here's a couple little ways to figure it out. If the y values are being added or subtracted, so if you notice that the x values are going up by 1 every time, this is supposed to be a negative. Those x's are supposed to be a negative. I think the font is wrong with it, but -2, -1. So -2, -1, 0, 1, 2, they're going up by 1s. And if you notice, it's going up by 3s, 1 to 2. It's going up, or -1 to 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11. Because these guys are going up in the same fashion, they're both going up consistently by the same number over here, the same number over here, that means that it's going to be linear. That's how you decide looking at its table. Exponential, on the other hand, the y values are being multiplied. So if you look at this, if I go from -2 to +1, or excuse me, -2 to -1, 0, 1, 2, these guys are going up by 1. But if you notice that the y values, if you multiply 0.25 times 2, you get 0.5. If you multiply 0.5 times 2, you get 1. If you multiply 1 times 2, you get 2. And if you multiply 2 times 2, you get 4. So if you're multiplying this, each one of these by the same number to get to the next consecutive one, then we know it's going to be exponential. In quadratic, this is tricky, but the second, whoops, see, bear with me, the second y values are being added, and it's getting cut off, but subtracted down here. So when you subtract these out, when you go 1 to -1, that means you're subtracting 2. When you go from -1 to +1, you are subtracting 2. When you go from 1 to 7, you're adding 6. 7 to 17, you're adding 10. Well, this doesn't look like multiplying by the same number every time, and it doesn't look like you're adding or subtracting by the same number every time. So go out one more set. So how do I go from -2? I think that's supposed to be negative, oh, that's a positive. So -2 to +2, they add 4. +2 to +6, we add 4. +6 to +10, we add 4. Notice the second differences are going up by the same, adding or subtracting by the same number every time. That right there is the indicator that it's going to be quadratic. So if you rule out exponential or linear, then go out to one more, subtract out one more time and see if these numbers come out the same. If they do, you can say it's quadratic. If they don't, then you're going to say it's none of the above. Which type of function best models the data in the table? Write its equation. All right, let's first graph the points. So this is going to be a little tricky because my graph is so small, but 0, 0, 1, 0.5, 2, 2, 3, 0.5, whoops, 3, 4.5. Wow, it looks like it's progressively going up fast. 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8. That looks exponential to me visually, which means it's going to be in the form of, which is right here, I was just about to write it, of y is equal to ax squared. We know it's exponential also by looking at this. If you, going back, don't forget exponential means that you are, the y values are being multiplied by the same number. So let's go back here. Let's see, 0 to 1 would be 1. So I'm looking at this. I know these guys are going up by 1s every time. And multiplying would say that it's exponential, which is what it's kind of looking like to me, but there's nothing I can multiply by the same to get from 0.5 to 2 and 2 to 4.5. So it looks like it's not going to be exponential. So therefore, let's try finding the differences. These guys are 0.5 apart. These guys are 1.5 apart. 2 to 4.5 is 2.5 apart. And 4.5 to 8 is 3.5 apart. Well, none of these are the same, so we know it's not going to be linear, so let's go out one more time. How far is 0.5 from 1.5? It's 1. How far is 1.5 from 2.5? That's 1. And these guys are 1. So because we went out on the second one, we know it's going to be quadratic. So it's not exponential, which is what my brain was thinking. It's actually going to, the other half of the parabola is going to be here. They only showed us half of it with the table. So it's definitely a quadratic equation, which is y is equal to ax squared plus bx plus c. We're going to look at only the first part of it, because it gets a lot more complicated, and look at the as an incomplete quadratic. Let's figure out, we know the vertex is at 0, 0, right? That's right here. And we're going to use y is equal to ax squared to find a. So we're going to go ahead and substitute that in. I can pick any of my points to figure out. So let's pick a point. Let's use 2, 2. So if I do that, that's going to be 2 is equal to a times 2 squared. Whoops. 2 is equal to 4a. Divide by 4. And a comes out to 1/2, 4.5. Whichever way you want to write it. So therefore, that's how you find a, which is going to be y is equal to 0.5 times x squared. I know that it's going to be 0, 0, which means that the plus c part is going to be plus 0. That's why that gets canceled out. You can go ahead and test it to make sure that you're right. So you would put, like, say 4 in the 8, plug that in. Does 8 equal half of 4 squared? 4 squared is 16, and half of 16 is 8. So that's a check to show that it actually, the equation that we just built actually works. So be careful, because if you think too quick like I did, you may think that this is exponential because it's only showing half of the parabola. That's what fooled me. It's really quadratic, and your table will solidify that.